Light looks simple. You flip a switch, the room brightens. You see objects because light hits them and reaches your eyes. It travels straight, reflects, refracts, predictable. But every one of those ideas fails the moment you look closely. Light doesn't always travel in straight line. It doesn't take a single path. It doesn't even decide where it is until it interacts with something. Send one photon at a time through two openings and it behaves like a wave. Force it to choose a path and it behaves like a particle. Ask a different question and the past itself seems to rearrange. This is not metaphor, it is experimental fact. Light refuses to behave like an object moving through space. Instead, it behaves like nature, calculating possibility. The strange part is not that light is complicated. The strange part is that reality allows something that is neither particle nor wave, but produces both when questioned. Understanding light does not just change optics. It changes what you think it means for anything to exist at all. If you throw a ball across a room, you know what it does. It leaves your hand, follows a path, and lands somewhere. At every moment, you can imagine where it is and where it is going next. This is the deepest expectation your mind has about motion. An object occupies one place at a time and moves continuously through space. For centuries, scientists believed light must behave the same way. After all, light travels from the sun to earth. It leaves a bulb and reaches your eye. It reflects from a mirror and bends in water. Everything about everyday experience suggests it moves like a very fast particle. And then an experiment broke that picture completely. Two openings. Imagine a wall with two narrow slits and a screen behind it. If you shoot tiny particles, grains of sand at the wall, each grain passes through one slit or the other and makes two piles on the screen. Nothing mysterious? Now replace the grains with water waves. Water spreads, passes through both openings at once, and produces a striped interference pattern, bright and dark bands, where waves reinforce and cancel. Particles give two bands. Waves give many bands. Simple. So scientists sent light through the slits, expecting one of these behaviors. The result forced physics to rethink reality. The pattern no particle can make, instead of two bright regions, the screen displayed a series of alternating bright and dark stripes, exactly the pattern waves produce. So light must be a wave. For a while, that seemed final. The wave theory explained reflection, refraction, and interference beautifully. The problem looked solved. Until someone asked a smaller question, one photon at a time. What happens if you send light so weak that only one particle passes at a time? Surely interference requires many waves overlapping. But when experimenters reduced the beam to individual photons, something astonishing occurred. Each photon hit the screen at a single point like a particle. Yet after many photons arrived, the full interference pattern appeared. Every photon contributed one dot. Together they formed a wave pattern. This means each photon somehow interfered with itself, not with other photons, with itself. The impossible conclusion: a particle should go through one slit or the other. A wave can go through both. The photon behaved like both at once. But we can push the puzzle further. Place a detector at one slit to see which path the photon takes. The interference disappears. Now the pattern becomes two simple piles-particle behavior. Nothing else changed. Just asking the question altered the result. The first realization: light does not have a single fixed nature. It does not carry a definite path before measurement. Instead, it follows rules that produce either wave-like or particle-like behavior, depending on the experiment performed. The photon is not switching forms. Our questions determine which aspect becomes real. And that is the first hint that light is not traveling through space the way objects do it, is exploring possibilities until interaction forces an outcome. A single photon creates an interference pattern, the kind only waves should make, yet it always arrives as a single localized dot. It behaves like it travels through both slits, but is detected at one point. Already strange. But the next experiment makes it stranger. Closing one slit. Imagine performing the double slit experiment again. Two slits open, interference pattern. Close one slit, pattern disappears. That part makes sense. But now, reduce the light intensity so only one photon exists in the apparatus at a time. Each photon leaves the source, travels toward the wall, and hits the screen. Yet the final distribution depends on whether the second slit is open. Even though the photon cannot interact with another photon, there isn't one. So the photon's behavior depends on a path it did not take. Trying to watch the path. You might suspect the photon secretly goes through one slit, and we just don't know which. So we place detectors at both slits. Now every photon is seen passing through one slit or the other. The interference vanishes. Two piles appear. The mere possibility of knowing the path destroys the wave pattern. Not disturbance information, delayed choice. Physicists push this further. They arranged the experiment so the decision to observe the path was made after the photon had already passed the slits. The result still changed. It behaved as though its earlier behavior depended on a later measurement. This does not mean the future affects the past. It means the photon never had a definite past until the measurement defined it. Light does not travel as a tiny object following a hidden trajectory. Instead, physics calculates all possible paths simultaneously and predicts the probability of detection. Only the final event becomes definite. The photon's history is not a story that existed. It is a set of possibilities consistent with the measurement. Up to now, light refuses to behave like an ordinary object. A single photon can produce a wave pattern. Knowing its path changes the result. Its past is undefined until measured, so you might think light is really a wave, and the particle idea is just a convenient illusion. For a time, physicists thought exactly that. Then another experiment forced them to abandon the wave picture too. The metal surface. Shine light onto a clean metal plate. Electrons jump out of the surface. This is called the photoelectric effect. At first glance, it seems simple. Light carries energy, the metal absorbs it, electrons escape. But careful measurements reveal something impossible for a wave. Intensity does not matter. If light were a wave, brighter light should deliver more energy per electron. Instead, brightness only changes how many electrons are emitted, not how energetic they are. Even extremely intense low-frequency light cannot eject electrons at all. Yet very dim high-frequency light ejects them instantly. No delay, no build-up. Each electron receives energy in a single, discrete event. Packets of energy. The only explanation. Light arrives in individual packets, photons. Each photon carries energy proportional to its frequency. If the photon's energy is high enough, an electron escapes immediately. If not, no amount of brightness helps. Light behaves exactly like particles delivering specific energy quanta. Wave and particle together. Now the contradiction becomes complete. In interference experiments, light behaves like a wave, exploring multiple paths. In the photoelectric effect, it behaves like a particle delivering localized energy. It is not switching forms. Both behaviors are always present. The equations predicting interference also predict energy packets. Light is neither particle nor wave. Those words come from everyday experience and fail at atomic scales. Light is something more abstract, an entity described by probability amplitudes whose interactions appear particle-like and whose propagation appears wave-like. The behavior depends on what aspect of the interaction the experiment forces to become definite. So far, light has broken every familiar rule. It behaves like a wave and a particle at once. Its past depends on how you measure it. It travels all possible paths until interaction fixes an outcome. But there is another behavior, even stranger, and it happens before quantum mechanics even enters the story. Light refuses to follow the ordinary rules of motion. The classical expectation in everyday life speeds add. If you walk forward inside a moving train, someone standing outside measures your speed as the train's speed plus your walking speed. Throw a ball forward in a moving car, and the ground observer sees it moving faster than you do. This seems unavoidable. Motion is relative. So if a light source moves toward you, you should measure light moving faster than normal. If it moves away, slower. For centuries, everyone assumed this without question. Experiments proved the assumption wrong. Measuring light. Physicists carefully measured the speed of light from sources moving at different speeds. They measured it on Earth while the planet moved around the sun. They measured it from moving mirrors and rotating devices. Every time the result was identical. Light always moved at the same speed. Not approximately, exactly. No matter how fast the source moved, no matter how fast the observer moved. The collapse of intuition. This result destroys ordinary ideas of space and time. If speeds add normally, the value must change. But the value does not change. So something else must adjust. Einstein realized what changes is not the speed of light, but our measurements of distance and time. Clocks tick differently in motion. Lengths contract in motion. These effects exactly compensate so that the speed of light remains constant. Light does not adapt to space and time. Space and time adapt to light. Light is no rest frame. Everything else can be at rest relative to something. A car can match your speed. A ball can be caught. Light cannot. No observer can move alongside a photon and see it standing still. For light, time does not pass in the usual sense between emission and absorption. This is not philosophical, it follows directly from the equations. Light does not travel through space and time the way objects do. It defines the structure of space-time itself. The universe arranges measurements so that light speed is invariant, even if that means altering distance and duration. Light refuses to behave normally because normal motion is defined relative to it. By now, light has already overturned ordinary ideas of motion. It does not choose one route before measurement. It does not behave purely as a particle or a wave. Its speed never changes, no matter how you move. You might think gravity at least would be simple. Gravity pulls things downward, but light refuses even this. Gravity does not pull light in the usual sense, because light has no mass. And yet light bends around stars. The old expectation before relativity, gravity was imagined as a force acting between masses. No mass, no force. So light passing near the sun should continue straight, unaffected. But Einstein's theory predicted something else. Gravity is not a pull, it is curvature of space-time. Objects follow the straightest possible path in curved geometry. Even light. The eclipse experiment, during a solar eclipse, stars near the sun become visible. Their apparent positions shift slightly. The shift exactly matches the amount predicted if space-time itself bends. Light does not curve because something grabs it. It travels straight, but space is not straight. The shortest path through curvature. Imagine drawing a straight line on a globe. The line curves relative to flat paper, but remains the straightest path on the sphere. Light follows similar straight paths in curved spacetime. From its perspective, it never turns. The geometry turns. Gravity slows time. Near massive objects, time flows differently. Clocks closer to Earth tick slower than clocks far away. Because the speed of light must remain constant, changes in time automatically change paths of light. So bending of light is not a force acting on it. It is the result of how space and time arrange themselves. Light does not move inside the universe the way objects move inside a room. It traces the structure of space-time itself. Where space-time curves, light's route curves without any push or pull. We've seen light refuse almost every ordinary rule. It is wave and particle together. Its speed never changes. Gravity bends space instead of pulling it. But now comes the strangest behavior of all, and the one that reveals what light really is. When light travels from one point to another, it does not choose a single route. It takes all possible routes at once. The ordinary idea of motion, in daily life, motion means a path. Throw a ball, there is one trajectory. Drive a car, you follow one road. Even if the route curves, it remains a single continuous history. So when a photon leaves a source and hits a detector, common sense insists it must have followed one path in between. Quantum physics says this question has no answer. Adding arrows. The correct way to predict light's behavior is to assign a tiny arrow, a probability amplitude, to every possible path the photon could take. Straight lines, curved paths, paths bouncing off surfaces multiple times, even wildly indirect routes. Each path contributes a small rotating arrow. When all arrows are added together, they determine the probability of detection at a point. Where arrows reinforce bright regions, where arrows cancel darkness, this reproduces interference perfectly. Why straight paths dominate? You might ask, if light explores all paths, why do we usually see straight rays? Because most paths cancel each other. Only near the path of least time do the arrows align strongly. So classical straight line motion emerges as the average of many possibilities interfering. The ray is not the real path. It is the most probable outcome of all paths. A photon does not travel a route and then arrive. The universe calculates all possible histories, and the event appears where the combined probabilities allow it. Light behaves strangely because it is not moving like an object. It is the manifestation of a rule connecting possibilities. We began with a simple observation. Light refuses to behave normally. It acts like a wave and a particle. It explores multiple paths. Its speed never changes. It bends with space-time rather than being pulled. Now we arrive at the deeper conclusion. Light behaves strangely because reality itself is not what common sense assumes. Objects versus events. Common sense tells you the world is made of things, objects, with definite properties moving through space. Quantum physics tells you the world is made of interactions, events, where possibilities become actual outcomes. A photon is not a tiny object flying through empty space. It is an excitation of an electromagnetic field, a process. Between emission and detection, there is no definite particle traveling somewhere. There is a calculation of possibilities. Why light reveals everything. Light is the simplest quantum object we can observe easily. Because it travels fast and interacts subtly, its behavior exposes the structure of quantum mechanics clearly. It shows that paths are not fundamental, properties are not permanent, measurement is not passive. Reality at its core is relational and probabilistic. The classical illusion, why does common sense survive? Because large numbers of photons and particles average into stable patterns. Interference effects cancel in daily life. Probabilities sharpen into near certainties. At large scales, objects behave as if they have definite positions and paths. But that certainty is emergent. Light refuses to behave normally because normal behavior is a large-scale illusion. At the smallest level, the universe does not consist of objects traveling along tracks. It consists of amplitudes interfering, probabilities forming patterns, and events emerging when interactions occur. Light is not confused. Our expectations are. Quiet ending. When you turn on a lamp, you do not release tiny glowing bullets. You release a quantum field oscillation that explores every possibility and resolves into events when it touches matter. Light behaves strangely because reality is not built from things. It is built from rules, and light is the clearest demonstration that those rules are deeper than intuition.